Hello everyone, my name is Jiang Haiteng and I come from Data Bucket Technology in Beijing. Today, I would like to share our work in Interspeech, a mask-based model for Mandarin Chinese polyphone disambiguation. Here is the typical pipeline of the text processing of Mandarin text-to-speech system. As shown in the slide, there are four modules in the pipeline: the text normalization, the word segmentation, and the polyphone disambiguation, which is also the module we focus on in our work. And finally is the episodic structure prediction. The polyphone disambiguation serves to predict the corresponding pinyin for the input polyphonic characters in the Chinese TTS system. And the polyphonic disambiguation is an essential part of the Chinese TTS system. However, the conventional TTS system would cause the following two situations. Firstly, the conventional system would predict the pronunciation belongs to unrelated polyphonic characters sometimes. Besides, the conventional system suffers from the imbalanced distribution of the pronunciation inside of the dataset. To end up the problem we mentioned before, we propose a Weighted-softmax function to prevent the prediction per the outside of the candidate range. Besides, we also add unconfident hyperparameter methods in the focal loss to ease the influence of the imbalanced distribution inside the dataset. Here is the input feature of our model. There are totally 6 features we use. It includes the Chinese character, the Chinese word segmentation, the part of space feature, and the polyphonic characters, the flag token, and finally is the mask vector. As in our paper, the flag token range from 0 to 2, which indicated that the input character which is disambiguation needed or not. As for the mask vector, the mask vector will be applied in the Weighted-softmax, and the Weighted-softmax will be introduced in the later characters. And here is the modern architecture of our model. The input sentence will first fit into the character level feature embedding layer. The input character will be turned into embedding vector, and then the context feature encoding layer, which constructed by BLSTM and CNN, would turn the embedding vector into the feature vector. And finally, the restrict output layer would predict the pronunciation sequence of the input character sequence. To compare with the initial modern architecture, we change the softmax function into the Weighted-softmax. Besides, we replace the loss function from the cross entropy to the modified focal loss. Both of the Weighted-softmax and the modified focal loss were applied in the restrict output layers. As for the Weighted-softmax, the probability of each element is calculated as the right side. For each polyphonic character, the candidate range of pronunciation is only occupy a small part of the entire pinyin set. If we use the initial softmax function as the left side, that will cause the case that the model may output the pronunciation which is not belongs to the input polyphonic character, and in this way, the TTS system would cause the additional errors. So to end up this problem, we add a mask vector in the initial softmax function, and that is our Weighted-softmax. In the right side, the MI denotes the mask vector of the input characters. Each impairment would multiply a Boolean value to decide if the pronunciation is masked or not. Every input polyphonic character would In this way, every input polyphonic character would only predict the pinyin inside of its candidate range. And here is an example to show the effect of the weighted softmax. As we can see that the correct pronunciation of the input polyphonic character is zhong, and its candidate pronunciation is zhong and zhong. As for the softmax function, the modern prediction is huang, which is not reasonable at all. And as for the weighted softmax, the prediction is in the right side. The weighted softmax, the prediction is zhong, and it can correctly predict the right pronunciation of the input polyphonic characters. The another contribution of our work is modified focal loss. Firstly, we introduce the focal loss. In the left side is the focal loss function, and in the right side is the figure of the focal loss with the different parameter gamma. As we can see that to compare with the loss function cross entropy, the focal loss function decays the loss value of all the example, despite the example is easy classified or is difficult to classify or not. It's not reasonable, and to address these questions, we add a hyper confident parameter alpha into the focal loss. The confident parameter alpha denotes the difficulty of the example, and as shown in the right side, if the output probability is greater than alpha, the input polyphonic character is considered easily to classify, and the loss value of the input character would be decreased. On contrary, if the example probability is less than the confident parameter alpha, the input character would be considered difficult to be classified. And in this way, the loss value of the input character would be enlarged. So the model would be focused more on this type of case. And here is the illustration of our data set. As in our experiment, the distribution of our data set is as follows. There are almost 70,000 sentences in our data set. And besides, in our data set, we contain 180 polyphonic characters. As shown in the table below, the distribution inside some polyphonic character is imbalanced, such as the polyphonic character liang. The pronunciation of liang appears 5,402 times in the training data set, and at the same time, the pronunciation of liang only appears 156 times in the training data set. The same situation also appears in the polyphonic character dang and xiang. So it can see that there are some polyphonic characters suffer from the imbalanced distribution. And to examine our idea, we implemented the following 5 systems to compare the performance of different systems. The BLSTM denotes the model only applied the BLSTM as the encoding layer. The BCNN denotes that we use the bichannel encoding layer which is constructed by BLSTM and CNN. The BCW denotes that we use the bichannel encoding layer, and the Weighted-softmax. The BCF denotes that we use the BLSTM and CNN beside with the focal loss. Finally, BCWN denotes that we use the bichannel encoding layer, and we also applied the weighted softmax and the modified focal loss. As we can see in the table, the final system get the best performance among 5 systems. And as for the imbalance distribution, we can clearly see that the modern which use modified focal loss and the weighted-softmax get the best performance among 3 systems. As seen in the polyphonic character Liang, it can get the best performance among 3 systems. So finally, let's make a brief conclusion. The weighted-softmax can prevent the model from predict outside of the candidate set of the input polyphonic character. And besides, the modified focal loss can ease the influence of the imbalance distribution of the pinyin set and the input polyphonic character. So that's all I want to share, and thanks for listening. That's all, and thank you.